Hi there, myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question.
The problem is strict permutation. Let's have a read at the question. You are given an integer n. You have to find a permutation of length n that satisfies m conditions of the following form. It means that, let's say we have this array whose elements range from 1 till n. We have to find a permutation. It means we can arrange the elements in whatever manner we seems fit till it satisfies m certain conditions. Let's see what those conditions are. So we are given a tuple of xi and yi, denoting that the element xi that will range from 1 to n must appear in the prefix of length yi. Formally, if the index of element xi is ki, then the condition is ki should range from 1 to I. Now, what does that mean? Let's see. Let's take an example that we have 7 elements, right? So we have 1, 2, 3, 4, 5, 6, and 7 places in our array. We have 1, 2, 3, 6, and 7. Let's say our condition is 2, 5. What this would mean is this is our index 5. Now we can place our 2 at any index that is in between 1 to 5, including them. So it simply means that we are bounding our permutation. As you saw, that we can have any arrangement, right? That's what a permutation means. But this is a condition that when we say 2 comma 5, we can only place 2 in index that are less than or equal to 5. Now, if no such permutation exists, we'll simply print -1. But if that's not the case, we will print the lexicographically smallest one. Now let's understand what does lexicographically smallest one means. Let's continue using the same example, right? So let's say we have some answer, right? We have some sequence that is our answer. So let's say we have x, y, 2, and z. Let's add this. I'll just draw z differently, right? Just think that this is z. So let's say this is our one answer, and this is another answer. We have x, 2, y, and at the end we have z. So in both of these answers, A and B, B is the one that is lexicographically smallest one. Why is that the case? To understand it in simpler terms for our solution, let's just say that we want all the smaller values to come first. So like there can be multiple answer, like this is also valid, this is also valid, but we want to make sure that the smallest elements come first. Knowing this should be enough to get our solution. Let's see what is the input format. The input format is standard. We have t-test cases. Then in the next line, we have n and m. N representing the number, the size of our array, and m representing the number of conditions. In the next m lines, we will have our condition, that is x and y, the tuple that we saw. The output format is that if there is no such answer, if there's no answer that exists, we will simply print -1. But if there is an answer, we will simply print that permutation. Now, the constraints are as follows. Our test case will range from 1 to 10 raised to 5. N, M, X, and Y all have the same condition. And another one is that Xi and Xj won't be similar. Won't be same. It simply means that if we are given this condition, right, we have 2 comma 5, we are assured that we won't have 2 comma 7. Like even if this condition are valid, right, if 2 exist on any index that is less than equal to 5, it will automatically will exist in index between less than or 7, right? But we cannot have both of them, right? In short, xi won't repeat. These were the constraints, and this is the sample input. Now let's take the fourth example. In this example, we have n as 5 and m as 2. This means that we have an array of elements 1 till 5. So as we saw, we can produce any permutation, right? So initially there is no condition where a particular element can be placed. So we can simply say that for any element, we can place it at any index that is less than or equal to n. And in this case, n is our 5. So what we can do is, we can simply write, let's say, our numbers, that are 1, 2, 3, 4, and 5. And this is the conditional index, right? Initially, at what index, or what is the index where they can be put? So initially they can be put at any index that is less than equal to n, right? For all of them, they are n. In short, we can place them at whichever index we seem fit. But then we have m conditions imposed upon them. So we have that 5 should be placed at an index that is less than equal to 4. Similarly, for 3 should be placed at an index that is less than equal to 2. Now that we have these conditions, let's try to form our permuted array. Now, to do that, let's first make a 2D matrix, right? In our 2D matrix, let's have let's have our indices, right? So if we have 1, we have 2, 3, 4, and 5. Now, what would this 2D index actually mean? Let me just draw the boundaries. So we are going to put all the numbers who wants to be at less than or equal to at this index. So initially all the numbers wants to be at an index less than or equal to 5. So we have 1, 2, 3, 4, and 5. So this is the initial condition, right? Initially all the numbers wants to be at an index less than equal to 5, because as we saw we can rearrange them in any way we seem fit initially. Now let's apply the conditions that we saw. So 3 will skip buckets, right? No, initially 5 will skip the bucket. 5 will say, hey, put me in the bucket of 4. So 5 wants to be put at an index that is less than equal to 4. Similarly, for 3, we'll move to this bucket. Now that we have this 2D array where we know that what is the particular index where the numbers wants to be. So let's create a resultant array, right? This is our resultant array. These are the index 1, 2, 3, 4, and 5. We'll draw the seeds for them. Now, as we know that we want to create the lexicographically smallest answer, right? So let's take this example for the fifth seed, right? For this seed, what are the fifth index? We have three numbers, right? We have 1, 2, and 4. Now, if I place 4, it will still be the correct answer. If I place 1, it will still be the correct answer. But as we saw the definition, we want the larger numbers to be at the back and the smaller ones to be at the front. Now, to deal with this, we are going to create a priority queue, right? And the condition for our priority queue is that we will have larger elements at front, right? So we will traverse here, right? So at index 5, what are the numbers that wants to be seated here? So we have 1, 2, and 4. Well, let's put them in the queue. We have 4, 2, and 1. Well, since 4 is the largest one, we'll pop it out and give it the seed of fifth index. Now we go to index 4. What are the numbers that wants to be seated at 4? Well, that is 5. Let's put it in the queue. We put it in the queue. 5 comes at front. We pop it. We put it in the seat 4. Now we come to index 3. Are there any number that wants to be placed at seat 3? Well, we can't seem to find them from our 2D array. Now, here comes a special edge case. Now, from this we can see that no number wants to be seated at 3. But are there any number that that is totally fine with being seated at 3? So in this case, we have our 2 here, right? So initially, 2 wanted to be seated at any index that is less than equal to 5. That means 2 will have no problem to be seated at 3. But here comes the edge case. If we had our priority queue empty as well as no number found in our 2D array, we can say that the answer will be -1. Why? Because we will have a seat that will go empty and we cannot let that happen. So if due to any condition such scenario occurs, we will simply say that our answer is -1. Now, in this particular seat, for seat number 3, we have 2. We'll place 2 there. Since 2 is totally fine at being any index that is less than or equal to 5. Now let's move to seat 2 or index 2. At index 2, oh sorry, I think it should be 3. So at index 2, 3 wants to be placed. We put 3 in our priority queue, and voila, 3 is actually the larger one among the queue. So 3 will get placed at 2. Now we move to index 1 and we see that there are no numbers present here. So then we go and look in our priority queue. We have our 1 here, right? We pop it out and place it in a resultant array at seed 1. And now this is our answer. So if you see, this is not only valid but also lexicographically smallest. Why? We could have placed 2 at index 1 and 1 at index 3. That would have been a totally valid answer, but that would not have been the lexicographically smaller one or lexicographically smallest one. So to make sure that our answer is lexicographically smallest, we make sure that all the larger numbers go at the back and the smaller ones come at the front. I hope you have understood the explanation. Let's just have a quick summary. So what we do is we first assign all the numbers the condition that they can be placed anywhere, right? So they can be placed at any index that is less than equal to n. Once we are done with that, we create a 2D matrix representing this, right? So we have 1, 2, and 4 wanting to be placed at an index less than equal to 5, so on and so forth. Now, since we want to have the lexicographically smallest answer, we create a priority queue to make sure that all the larger numbers are placed at the last indices and all the smaller ones at the front. So even though at index 5 we had numbers like 1, 2, and 4, all of them, uh, you know, that would have not minded or actually wanted to be placed at 5, but we place the largest one at that index. We go on and we fill all the other indices. Then we saw the edge case. That is, in case any seat goes empty, that we cannot find any number that wants to be seated at that place, or that is fine by being seated at that place, we simply say that since this particular seat will go empty, we'll have no answer. So our answer is that -1. I hope you understood the problem and the approach to solve it. In case you still have any doubt, you can ask them to our doubt solvers. Let me give you a tour on how you can do so. Move to practice problem section. Once you are there, choose a problem that you want to solve. Let's say you got stuck on this particular problem, that is bidding. Just open the problem and here you can go to ask a doubt. Then in the bottom left corner, you will see a widget that says ask a doubt. Just click on it. You can say, hey, start a new chat. Once you are there, you can type whichever question that you have. So let's say we want to ask, what are constraints? Right? Just click enter. And one of our doubt solvers will definitely solve your doubt instantly. So whenever you're stuck on a question, that is, you are stuck on a TLE or are not able to get an AC, feel free to ask your doubts to our doubt solvers and you will definitely get an answer. Let's see the C++ implementation of solution for this particular problem. So we take 3 test cases and for each test case, we run the function solve. So as you remember, first we make the nums array, right? So for all the numbers that are there, we say that, hey, initially all of them wants to be placed anywhere, right? We can rearrange them and we can put them at any index that we want. So that is that. Then we create the 2D array that you saw, right? That is named behind here, right? So we'll put all the number that wants to get behind any particular index. So we take x and y. Now, initially, x had the condition imposed on it that it can be placed anywhere less than equal to n. But now that is not the case, right? So we make it 0. That hey, x has a new condition imposed and it cannot be placed anywhere less than equal to n. Then for y, right, x actually wants to be get placed at an index less than equal to y. So for y, we push x. Once we are done imposing all the m conditions, for all the other numbers, we will say that, hey, if you have not been placed under any other condition, I will simply put you behind any index that is less than equal to n, that you can see from here, right? As you can see from here, For all the other all the other numbers, we can place them at any index less than equal to n. Now this is our priority queue. Now, as you saw, we start moving from the last index, right? So for index n, let's see what are the numbers that wants to be placed at this index, right? So we push them in the priority queue. Now, if our priority queue is empty, right? As you saw the edge case, if our priority queue is empty, we simply see that no answer is possible, -1, and return. But if that's not the case, we will take the largest number, right? As you saw, priority queue will keep the largest number at the front. So we place the largest number at ith index, and our I is starting from the last index, that is n. So at n, we find all the bunch of numbers that wants to be placed at n, and we take the largest among them and place it at that index. Similarly, we go for all the other indices, and at the end, we simply print our permutation. This was the C++ code, and as you can see, I have gotten the AC. Similarly, we have written the code in Python. So I take all the test cases. Then for each test case, I'm taking n and m. Then again, I'm creating the same nums array. Then the behind array. This is same as I have done in C++. Only thing different here is the implementation of priority queue. So now I have done the same thing till here, right? As you can see, till here, everything is same. I created the behind array, that is my 2D matrix. I placed all the other numbers who had no restriction or conditions imposed upon them, and I imposed the condition that they have to be placed anywhere that is less than equal to n. Then for priority queue, I'm using heap queue. You can learn more about them, and you can find many articles. I will just give you a quick summary. So by using heap queue, you can simulate priority queue, but it will be an ascending order. So right, smallest element would be at the front. So to deal with that, what we can do is we can simply multiply the numbers by -1, making that all the positive numbers that have the highest value will actually become the smallest one when multiplied by -1. So we do that. We push them in the priority queue. And when we want to pop them out, we simply multiply by -1 again. I hope you understand this concept. And at the end, I'm again printing my permutation. And as you can see, it has given me a 100% correct AC. I hope you have understood this problem. And if you have any doubt, you can ask them in the comments, or you can use the doubt solver feature on CodeChef. Have a nice day. I will see you in the next video.